David Nichols received his PhD in 1973 from the University of Iowa, followed by postdoc work in pharmacology. You carry on? Cross our fingers. Okay. He was the Robert C. and Charlotte P. Anderson Distinguished Chair in Pharmacology and a Distinguished Professor of Medicinal Chemistry and Molecular Pharmacology at Purdue University. He is currently an adjunct professor of medicinal chemistry at the University of North Carolina, Chapel Hill. So I'm going to pass you over to Dr. David Nichols.
Well, good morning or evening or afternoon. I'm not sure what time it is there. It's a little after 1 o'clock here. When Ben contacted me and he said, well, you know what they would really like to hear probably is some of your stories about what you did, because actually I was the longest functional. Can you hear me? I see somebody pointing to his ear. Too loud? No. Oh, okay. So I actually went to graduate school in 1969 specifically to work. Loud? Are you okay now? Yeah. Okay. So I went to graduate school in 1969, August of 69, to actually work on psychedelics. I went to the University of Iowa. There was a guy there named Joe Cannon, who was the head of the department, and he had been working on compounds related to atropine, which are pretty active CNS agents. Really, if any of you know anything about atropine, it just basically knocks you out of reality and very confusing. But he was the only guy I could find anywhere that was doing research in this field that was taking graduate students. So I went to the University of Iowa and I interviewed with Joe Cannon, and he worked to get me there and got me a fellowship and everything. And I said, well, are you still working on the BZ type compounds? He said, no, not working on those anymore, but I'll give you a project on apomorphine analogs. And I don't know if you know what apomorphine is, but it's a compound derived from morphine and makes you vomit violently. And he, for some reason, thought I was in a hurry to get out of graduate school. And he said, oh, you can make these compounds, you'll be in and out, you can get out and get a job, make money. Because I had a family, a wife and a small child. And I had been working full-time and going to school at night for 5.5 years. So I actually finished my bachelor's degree going to night school. So I'd get up and go to work a full day, and then go right to the University of Cincinnati, get a cold sandwich, heat it up in the microwave, and go to class until 10:30 every night. I did that for 5.5 years. So when I went to grad school, the idea of just doing research all day long with a couple of classes was really appealing. So Joe Cannon seemed to think I wanted to get back to that world, and I was really looking forward to graduate school as a kind of vacation. But this project on apomorphine was really pretty boring, and all the literature was in German, and I had to take reading German, but I wasn't real happy about it. So he said, well, now you can work for anybody in the department you want to work for. So there was another guy there named Charlie Barthnick who published nothing in the field of what we call psychedelics then. And so I talked to Charlie Barthnick, and he had a student who was making what he called mescaline metabolites. And so Dr. Barthnick showed me what this other student was doing. The student was really pretty incompetent chemistry-wise. He was doing things that made no sense at all and using the wrong kinds of chemicals. So I started having a chat with Barthnick, and he pretty quickly realized that I knew more about the field than he or his graduate student did. And since I had a fellowship already that paid my way, he was very interested in me as a graduate student because it wouldn't cost him anything. So we very quickly sketched out some ideas. I had followed all the literature in the field up to that point, and there really wasn't very much. Alexander Shogun had just published a paper in 1969 called Structure-Activity Relationships of One-Ring Psychotomimetics, which is a summary of the work he'd done in about the previous 3 or 4 years. And that was almost the whole of the field with respect to phenethylamine psychotomimetics at that time, which then they were hallucinogens, and now they're more or less psychedelics, but the same things. And so I had been thinking about this, and one of the compounds I thought would be really interesting to make was DOB, which was unknown at that time. And so I said, well, how about if I work for you, one of the things I could make is this compound, the bromo in the 4 position. So the bromine's about the same size as a methyl. And DOM or STP, and I don't know how much the audience knows about the field, but DOM or STP had made it big in the San Francisco Haight-Ashbury area in 1967. It was a phenethylamine that had a methyl group, and a bromine and a methyl are about the same size. I thought, well, we could put a bromine there, and it would be about it should be as active as DOM. And that was the key compound I wanted to make. And then I said, let's put bromines in a couple other places just to fill it out so we had our own publication. So he thought that was a cool idea. So he said, yeah, you can work for me, and then you can do this for your master's degree. And I finished those compounds in the first semester, and we started publishing on those. And then did a variety of other things. While I was a graduate student, I did enough chemistry to publish, I think, 16 papers. And I finished in 3 years, and which was kind of a record there in the department. And the department had for his students, he had a rule that nobody could have a thesis longer than 100 pages. He just wouldn't read them. And that was kind of weird. And so my thesis, I didn't work for him, so my thesis was 180 pages. But anyway, during the process of getting my PhD, I got to know the people in pharmacology. I was kind of a pharmacology groupie because I was interested in how these drugs were actually working. So I used to hang out in the pharmacology department. So some of the compounds I made, I took over, and we had a good relationship with the head of the pharmacology department. So I'd go over and I learned how to do some of the techniques and got to know the people in pharmacology. And as I was getting close to finishing up with my graduate work around December of '72, he had a graduate student named Jim Engelbrecht who was doing an MD, PhD. And Jim had been looking at the effects of some simple compounds on mouse behavior. And these were simple substituted benzene derivatives, things like oil of cloves, eugenol, and they had an anesthetic effect, but there was one compound he hadn't been able to get. And the student of Bartlett's had been trying to make it, and he had really screwed it up badly. And so I asked Jim to test some of the compounds I had made, and he said, oh yeah, I'd be happy to do that, but I'm running out of time. I have to get my master's because I'm going to start medical school. Could you make this compound for me? So I made a compound. It was really fairly simple to make it. And I made about 10 or 15 grams of it, crystallized it. Very large crystals, almost looked like rock candy, sugar candy. And I was thinking what I was going to do when I finished my PhD. And John J.P. Long was the head department, and he was the guy that was connected with the pharmacy school. And so I took this bottle of this compound over to give to Jim Engelbrecht. And back in those days, you didn't have word processors and graphics programs. And maybe some of you may remember there were these plastic rub-on letters. You would lay it was a sheet of plastic with all the letters of the alphabet structures. You'd lay it on a piece of white paper and rub on it, and it would transfer a stick. And so I made a label, a humorous label. I drew the structure, and I put the name of it. And then, since it had been so difficult for him to get the compound, I put the name of the chemical company. I made it up, and I said, the sheer grace of God Chemical Company. And so maybe somebody would laugh, but I didn't hear any laughs. Can you hear me? Am I still audible?
Yeah, we lost you for a couple of seconds there.
Okay, so, oh, you didn't hear what I put for the label, the chemical company that made the stuff?
No. Can you repeat that, please?
The name of the chemical company that made this material that's been so difficult to get was the Sheer Grace of God Chemical Company. So I happened to run into J.P. Long as I was going over to give this to Jim, and I gave it to J.P., and he knew that he had a lot of trouble getting this compound, and he looked at it and he saw that Sheer Grace of God Chemical Company. He just broke out in a big laugh. And I said, I've been thinking about doing a postdoctoral fellowship in pharmacology. Do you think that I could do that here? And he said, yeah, we'd love to have you. So I sort of immediately went from the pharmacy school to the medical school and did postdoctoral work in pharmacology. And then I tested some of the compounds I made. We mostly were looking at effects on cats and rats. I tested MDA and PMA at that time in mice and published a very early study on that. And learned a lot of pharmacology. And then I went to Purdue in 1974. And when you start out as an assistant professor, you wonder what you're going to do. And I just did a variety of kinds of things, but I continued the work that I had started at the University of Iowa in psychedelics, because usually when you leave a PhD and go start your own position, you don't keep the things you worked on as a PhD because they're often sort of the intellectual property of your professor. But in my case, everything we published was really my own ideas. In fact, he was promoted to associate professor based on all the papers that we had published. And so I kept working that field, and then I struck up a acquaintance with Sasha Shulman. He had actually come to the University of Iowa near my last year of graduate school and had given a seminar. And I hadn't been able to meet with him in any formal context, but I got an opportunity to drive in the car with him, so we drove him back to the Cedar Rapids, Iowa airport. And I had never met him before. And I said, Sasha, did you ever, well, I called him Dr. Shulman at that time, did you ever think of making a compound with a sulfur in that position instead of a bromine or a methyl? And because I had sort of developed a hypothesis that the compounds that were more visual had substituents that were more easily oxidized in the body, so that mescaline was a highly visual compound, had a methoxy. STP was still somewhat visual, had a methyl. DOB at that time, what I knew about it wasn't particularly visual, and I thought, well, maybe if we put something there that could be oxidized easily in the body, it would be more visual. So sulfur is something in the body oxidized pretty easily. So Sasha said, well, yeah, we tried to make it, but it all turned to tar, so we never did work on it anymore. When I started at Purdue, I ran across a reference that suggested that the precursor for that material could be made pretty easily. And so I actually made about 20 grams of the aldehyde starting material. And of course, I could have carried it on to the amphetamine or phenethylamine, but I had been in contact with Sasha, and I said, Sasha, I've got the starting material. Why don't we publish a paper together? I'll send it to you. You can convert it into the phenethylamine and the amphetamine, and we'll publish it. So we published a paper on sulfur analogs with psychotomimetic means, I think around 1976. So that was the beginning of the collaboration. I maintained a correspondence with Sasha pretty much until internet and email started taking over, and then we had actually less communication. But I made escalene and proscaline and isoproscaline. I extended the pair position of the mescaline analogs, and it showed that they were also quite active. And Sasha and I had a debate about whether the 2-carbon or 3-carbon compounds were more potent. And I said, Sasha, I think some of these 2-carbon compounds might actually be as potent as the 3-carbon compounds. And we had some disagreement about that, but then when I made escalene and proscaline, they were quite active in the 20 to 30 milligram range. So it's clear that you could make compounds that were active in the 2-carbon side chain if you had the right substituents on the ring. So then there was a fellow at Purdue named Peyton Jacob who had done a PhD with Nobel laureate Herb Brown, was doing a postdoc with Neil Castagnoli at UCSF. And Neil and Sasha were good friends. Neil let Sasha use his laboratory to run mass specs and NMRs and analytical data. And so Peyton was postdocing with him after we made this first compound, which would eventually was named Aleph-1. Sasha called me on the phone and said, Neil Castagnoli's got this young postdoc, and he'd like to make some compounds with the sulfur and move it around to different positions on the ring. And are you going to do any more sulfur chemistry? And I said, no, I think the ones with the sulfur in that 4 position are the only ones that are going to be interesting. So then Sasha went ahead and they collaborated with Peyton Jacob and Neil and made the sulfur in the 2 position and in the 5 position. And there were a whole series of compounds. You may know Sasha gave these compounds some really strange names like 2-tweetio and 3-tweetio and things like that. So those are all sulfur substituted compounds. And then he played sort of what I call musical methyl game. You've probably heard of 2CT2 and C2CT7, CT, I don't know how many numbers he got up to. Those were all sulfur compounds with a 2-carbon side chain. So really showed that the 2-carbon side chain gave compounds that could be quite potent, and especially when we put a sulfur in that pair position. So that was sort of the early years. Now, the interesting thing is, my postdoctoral mentor, J.P. Long, after I got a grant funded from the National Institute on Drug Abuse, said, Dave, I never thought you'd get money to work in this field. And I actually was funded for 29 years from the National Institute on Drug Abuse, just specifically to study hallucinogens. And so, without much competition in the field, we worked in almost all of them. We did tryptamine work and a lot of phenethylamine work. As you know, you've probably heard of dragonfly and bromo dragonfly and 2CB fly and things like that. Those all kind of came out of my lab. We made LSD analogs, FLAD and ALAD and ProLAD, which are more potent than LSD. we locked the diethyl groups of LSD. It has two ethyl groups that can swing, and the activity of LSD is so uniquely dependent on having two ethyl groups there that we thought that there must be a place in the receptor where those ethyl groups specifically bound, but how could we test that? So one thing we did was to take those two ethyl groups and we tied them into a four-membered ring that had a methyl group in two different positions. And so those methyl groups could be on the same side of the ring, on opposite sides of the ring this way, or opposite sides of the rings this way. And we made those three compounds. They're isomers, and only one of them had LSD-like activity. So it pretty clearly showed that when LSD binds to the receptor, those ethyl groups have to be in a very specific shape or conformation to activate the receptor. And at a certain point, in academia, you can't just make compounds. The Sachi had somewhat of an advantage because he could just go back in his lab and make whatever struck his fancy. But in academics, you had to actually have hypotheses about things. So for example, when we made a bromofly, a bromo dragonfly, etc., the hypothesis was that the oxygen atoms had to be oriented in a specific orientation in order to interact with the receptor. And I don't know how much chemistry you know, but had to be hydrogen bonded by serine residues in the receptor. And as we got into it more deeply, it became apparent that just doing the chemistry wasn't really going to be as explanatory as I needed it to be. And let me just ask a question now. I'm not sure what my time frame is here, time-wise.
So what time is it now? Should we run for another 10 minutes?
Yeah, I don't have a problem with that. I want to make sure that I just don't babble on incessantly and go over my time. Yeah.
Let's say for that 10 minutes.
Yeah, so we had developed hypotheses, but at a certain point in time it became clear that chemistry wasn't going to get us where we needed to go. And I've gotten a lot of email from people over the years saying, oh, I want to be a psychedelic chemist, and do what you do. And what I basically tell them now is, we have lots of chemicals out there. What we really need to understand is how they actually activate the receptor and what happens inside the cells, where they are, and how it all fits together to modify consciousness. So at a certain point I realized that chemistry was not going to be the be-all and end-all. We've done a lot of chemistry. You probably know some of the molecules in p-cal and even t-cal are things that we made in our lab, but of course I could never test them in humans. I always had lots of volunteers who wanted to test them, but I couldn't do that. Even when I started graduate school, I told people what I was doing, and people say, do you need anybody to test those molecules? I was going to do that. So we started getting in, we did behavioral work, of course, in mice and later in rats. So we had a behavioral model that we used in rats that were trained to detect the effects of LSD. That was the main model we used. And then we were doing a lot of receptor binding when we said, well, we can forget about what happens as it's distributed throughout the animal if we know what the receptor is. And when the receptor was identified, we could do receptor binding studies and get affinities. And then I really thought, we really need to know more about what's happening in receptors. So we published a couple papers where we actually mutated amino acids within the serotonin 2A receptor and then made changes in the phenethylamines that bound so we could determine how they were actually fitting to the receptor. But we actually know from phenethylamines now that there are two key serine residues that are in transmembrane helix 5, which is part of the receptor that engage these methoxy groups. With LSD, we know now that the diethyl group is interacting with a residue that's in what's called the extracellular group 2, that's a leucine. It pushes against the diethyl amide and forces it to go in a certain orientation. That's why the LSD diethyl amide group has to be in a specific orientation. We have a bunch of papers now that will be coming out probably within the next year. We've continued to model the crystal structure of the serotonin 2B receptor has just been published, and so now we've constructed a homology model based off of that. That's a serotonin 2A receptor. So we're hoping to take all the work we've done mutating these receptors, combine it with virtual docking, computer chemistry essentially, and really show how all these molecules are interacting. The next piece of the puzzle is what they actually do inside the cell. And I presented a talk at the Psychedelic Science Conference where I showed a heat map. It turns out that these receptors don't just turn on and off like a switch. When they turn on, they can turn on in sort of many different ways depending on what shape the molecule has when it binds to the receptor. So when the molecule binds to the receptor adapts itself to that molecule and adopts a certain conformation. And when it does that, there are pieces of the receptor that hang inside the cell, the intracellular part, that change their shape and interact with signaling components. And so if you put LSD into this receptor, it binds to the receptor in a certain way and produces a certain shape of those intracellular loops. When you put in mescaline, it binds in a completely different way and produces a different shape. So every one of these phenethylamines produces a different set of signaling molecules within the cell. So qualitatively, you could look at mescaline or 2CT7 or LSD or any of these. They're all activating the serotonin 2A receptor as a principal mechanism of action. But the signals that they're producing are different in terms of both quantity and quality. And that's the thing that nobody has really been able to completely elucidate yet. So that's a big piece of the picture. So essentially, from the beginning, just doing simple chemistry, trying to understand how phenethylamines like mescaline could bind to the same receptor that LSD binds to. Starting from that, working all the way through a computer-driven chemistry and basically drug discovery. I covered the whole gamut of things that were possible to do, and really we know quite a lot. So if I think about all the things that have happened since I started in 1969 working on psychedelics to the point now where we know a lot about the molecular biology of the receptor, the signaling in the receptor, and now you know there's a so-called renaissance in psychedelic research, a lot of which I consider that I helped to catalyze by making the MDMA that Rick Doblin has used for all the studies, as well as a lot of clinical research in the US, by making the MDMA, by making the DMT and working with Rick Strassman when he did his study with DMT, by making the psilocybin for Roland Griffiths in his first spirituality study and the psilocybin for the study he's using now. And then founding the Hefter Institute in 1993, which is now we have completed Charlie Grubb's clinical study of psilocybin in terminal cancer patients, and that was published. 2 more similar studies at New York University. That's backwards, but I can still read it. Yeah. And then you may or may not know, but we just completed enrolling all the subjects in a small study at University of New Mexico using psilocybin to treat alcoholics. And also Matt Johnson at Johns Hopkins has done a small study of smoking cessation, showing psilocybin therapy can keep people from smoking. So psilocybin is looking really good. And we filed now to reclaim the name indocybin. Sandoz had given indocybin as a name for psilocybin and they had abandoned it. So we've requested that that be reactivated for the name of psilocybin. We're now developing a GMP synthesis for psilocybin. We've been meeting with consultants for the FDA. And we think within about a year or so, we will be going to FDA and putting in a formal request to say, what do we need now to develop this further as a legitimate medicine. So from the point at which they were considered psychosis-producing drugs to the point now where they clearly have a substantial medical benefit. And I've seen this whole process. I could probably talk for hours about all the things that have gone on, but in this short venue, just to give you kind of a taste of some of the roles that I in my laboratory played in this process. And I'll stop there, and if there's time for questions, maybe you could ask me questions, and that would be helpful.
Okay, yes. If you have questions, it's probably best to come down and let you. Any questions? Just keep it to 2 or 3.
Hello. I wanted to know how you test the rats to see if they experience the LSD.
I gave a talk on MDMA very early on. We were the first ones to do pharmacology in MDMA in 1980, before anybody really heard of it or called it ecstasy. I went to a conference in California where I talked about it, and some other people talked. And then in the Q&A afterward, an individual got up and said, we've talked about all the, neurotoxicity and serotonin neurons, etc., but no one has talked about the spirituality and the spiritual aspects of MDMA. And Sasha was there, and someone else was there. And they looked at me and nobody would say, I knew that, and I said, well, my rats are all atheists. And so, monocular chamber that had two levers in the front, the right and left lever, and depending on what they were activated or not, the rats would get a little food pellet, a sucrose pellet, rat candy. And so we could train the rats by alternately giving them injections of placebo, saline placebo, or LSD, and turning on either the left or the right lever. We could train the rats so that, for example, when they got a placebo injection, it would only be when it pressed the left lever, it would get this little candy pellet. And when it got LSD, it would only press the right lever, for example. And so over a period of about 2 to 3 months, we could reliably train those rats so that any given day, if we gave them an LSD injection, they would go in and they would press the right lever. And we alternated right-left so that we count for handedness. And this is a very robust response. So rats would press 1,500 to 2,000 times in 15 minutes. It really would work for that. So then we would take those trained rats and we would develop a new drug and say, well, does it have LSD-like effects or not? We would give it to the rats. And if the rat pressed on the LSD appropriate lever, he was essentially telling us, I think you gave me LSD. And if he pressed the other lever, he was saying, I think you didn't give me LSD. And the power of that approach is that the rats only respond given something that has qualities like the training drug. So if we have a rat trained to discriminate the effect of LSD and we give that rat methamphetamine, the rat will press on the placebo lever. So we used that basically from 1984 until I really retired in last year to test compounds to see if they had an LSD-like effect. And obviously, that's a very weak echo of what happens in humans because all the rat is telling you is, I think you gave me LSD, or I don't think you gave me LSD. But although it gave a few false positives, basically you get a very good correlation with human activity and potency and the effect in rats.
We had Professor Nutt talking earlier on about these difficulties in researching these chemicals in this country. I just wondered, from the depth of your conversation now, how much difficulty there is in the States about funding and research, funding your research, and how much obstacles are put in the way.
And for most of my career, my research was funded by the National Institute on Drug Abuse. They had a basic interest in understanding how these drugs work in the brain, because anything that's not a prescription drug, they consider a drug of abuse if people take it. So how do they work? Clinically, that was the reason I started the Hefter Institute. I used to go to scientific meetings and sit and talk to people, and I'd say, we need clinical research, And they'd say, yeah, but nobody will fund it. And I'd say, you could get it, you could fund it, you just couldn't do it with government money. And you need an endowment, you need somebody to fund you. When I started giving that speech and, over a beer after a meeting, I'd say, you just need $1 million endowment. And then it was a $2 million. And then as years went on, it got to $3 million and $10 million. And somewhere in 1990, I was telling somebody that at a meeting, and I went home and I said, Dave, you're going to be telling the same story, you're going to be sitting in a rocking chair retired, and nobody's going to do it. You need to do it. So I called a bunch of friends of mine that were psychiatrists and psychologists that were interested and said, let's start an institute to study these and get private funding. So that led to the funding, the initiation of the Hefter Institute. We thought initially that the Silicon Valley folks who made all their money, and Steve Jobs said LSD was one of the most important things he ever did, and Microsoft, the people out there, everyone knows that the people in Silicon Valley use a lot of psychedelics. And we just thought that the money would come rolling. It was a very difficult process. We do have good funders now. We're getting about $2 million a year. And so it's private. We hope that when we get some more data that we will be able to go to the government and actually put in an application for money for a large multi-site trial. But funding has been the real issue, and I know Rick Doblin and MAPS has had the same issue, getting the money to fund these studies, because the government just has not recognized that they're anything other than drugs of abuse.
Thank you.
Hi. The last time Alexander Schultz in the UK talked about possibility of using MDMA for treatment of phobias. I wanted to know whether you know of any studies or any research, or whether you think
I don't know of any studies looking at phobias. We're just really getting into the clinical part of it. When people say somebody is dying and they have anxiety and depression, you give them psilocybin, and under the conditions we've been using, they lose their fear of death and they're not afraid to die. People say, how does that work? Well, I don't know. It could be a pharmacological thing. It could be a psychological, a combination of both. My guess is that with, I don't know about MDMA, but with one of these types of compounds, it might well be possible to treat phobias. We've talked about treating eating disorders, because there's a case where someone with eating disorder could, you could show a body image model with bulimia and say, look, you're killing yourself. And somehow those effects sink in when someone's been given a psychedelic. Spasticity, I don't really know. The mechanism of action for MDMA is a release of neurotransmitters. I don't know how that would particularly work there. And microdosing, Hoffman himself was a fan of microdosing with LSD, 20 or 25 micrograms sort of on a daily basis. And I know people who have done that and said, I feel like I'm brighter and I can do things and I'm sharper and so forth and so on. I haven't heard of microdosing with MDMA. The problem with microdosing with MDMA is that it's not a very potent compound to begin with. So you think of 125 milligrams as sort of a standard dose. You go to 30 milligrams or 25 milligrams. The effect is going to be very small, probably not detectable in most people. Whether or not that will have a salutary effect, I don't know. LSD is so potent, its affinity at that serotonin 2 receptor is 0.5 times 10 to its 9th molar. And if you go to 20 micrograms, you're still getting significant receptor occupancy in a whole human. So I think it's more a question of the relative potencies. But I don't really know what microdoses of MDMA do. And microdosing, you'd probably be talking about 20 or 30 milligrams, which is not close to an effective dose. But yeah, this is all unknown. I mean, hopefully we'll get more clinical research as time goes on and people recognize that these things do have medical potential. It'll be more of an interest. I mean, you've probably seen more of a public interest in the last 10 years than you've seen for a long time with respect to the value of psychedelics.
We'd better sign off there. We've almost run out of time. Thank you very much.
Thank you.